Thank you for the introduction. Uh, I'm Rahul Singh. I'm doing PhD under Professor Aparna Singh back in IIT Bombay, India. So today my topic of presentation is like I'll tell you about how the interlaminar spacing and the temperature affect the Charpy toughness of the ultra-fine perlite. So moving ahead, I'd like to tell you first of all what is a perlite and the morphologies and the different definitions of a perlite. So basically, perlite on a scale point of view, like application part, we use it in railway tracks and railway wheels for very high strength cutting tools. Also are made of out of perlite steels. Here you see the suspension bridge. The tension wires which are made in are used in that suspension bridge are made of perlite. So before this study from my co-workers have been done on high strength. So they have successfully made a perlitic steel which has a strength of around 2.5 GPa. So in this, my focus will be to study about the toughness. So moving ahead, I like to talk about the different definitions we have in a perlite. So initially, this is the dashed honeycomb structure is our prior austenite grain, and within that prior austenite grains we have multiple nodules, as you can see here. And that nodule there are multiple perlite colony. A perlite colony is something where the cementites are parallel to each other, so we defined it as a perlite colony. And into that colony we have multiple lamelles of ferrite and cementite. So this spacing between the ferrite and the cementite is termed at interlamellar spacing. So moving towards the experiment part, we got a steel of carbon 0.72. Actually, we casted this steel and then we blocked into three. We make a three block of that, and we further on we did the heat temperature. We first austenize it at 1000 degrees Celsius for 60 minutes, and then isothermally hold it for 725, 650, and 590 degrees Celsius for respective time. And then after polishing the sample and etching, we found this is for the 591, and this is for the 650, and this is for the 725. As we increase the isothermal temperature, we can see the spacing between the ferrite and the cementite is increased. And to measure the different like interlaminar spacing and the nodule size and the colony size, we have took multiple SEM images at multiple magnification. Here, with this help of this images and like images like this, we measured the interlaminar spacing. And and the SEM images at little lower magnification are used to measure the colony size, and we did the EBSD also to measure the nodule size. As we can see here, the specimen treated at the lowest isothermal temperature has the lowest interlaminar spacing, and the colony size is smallest colony size. But one thing we can see from this, like the perlite nodule size is similar because we are treating all three samples at the same austenization temperature for same time. So further moving, so after heat treatment, we made almost 15 samples from each block, and to and we subjected it to the Charpy test. And for our surprise, we found that at room temperature, the impact for the every sample, like all of that 555, that 15 samples are almost similar. But at as the temperature was increasing, we can see the impact energy at was higher for a specimen which was treated at a lower temperature, and same trend we observed at a higher temperature also. So here the values have been shown here, what is represented in the plot. So we were interested to know what phenomena is happening, like what is difference we are getting. Like at room temperature, we are not seeing any change in the impact energy for the three samples for the three conditions. But as the temperature is increasing, we were able to see, and we can make a prominent difference between them. So for that, we did the factography just below the notch of the sample at which were tested at 25 degrees Celsius. Here we saw big facets were formed in all the three conditions, and after the measuring the size of these facets, it was found that the facet size was similar to the nodule size. So as earlier I have shown, the nodule size for all the three specimens were same. So that's why we were not able to see any difference in the impact toughness at 25 degrees Celsius. But at 125 degrees Celsius, we can see the ductile region. This double-headed arrow is showing the ductile region, and this arrow is showing the crack propagation direction. We can see the smallest ductile region in the case of NP 725, that is treated at 725, and the biggest in the case of 590. One more thing is, at high temperature, this slips of a cementite gets activate. So that is the condition, that is the reason why we are seeing higher impact energy at NP 590 condition, and smaller in the case of NP 725. Further, when we see at 250 degrees Celsius, the ductile region is bigger compared to the 125. So it is the biggest in the case of NP 590, which is almost 5 times what we were getting in the case of 125 degrees Celsius. And this ductile region tell us like it will absorb more energy before the catastrophic failure. And that was also prominent from the plot what we saw earlier, where the impact energy at 250 degrees Celsius for NP 590 condition was the highest compared to NP 725 at that temperature. So further moving in from literature, it's very evident that the bending of cementite is a signature of heavy plastic deformation. So keeping this phenomena in mind, we further did the SEM at very higher magnification near the crack. So we observed in the case of 25 degrees Celsius, all three samples, we were not able to see any bending of cementite. We can see the crack propagation between the parallel ferrite lamellae. We could not see any bending of the cementite. But whereas in the case of 125 degrees Celsius, we were able to observe the bending of cementite, and here the bending of cementite is represented by the zone A. So we can see here the bending of cementite and then further rupturing. Whereas in the case of 250 degrees Celsius, the bending of cementite was more. We can see here the bending of cementite was more, and this is also a reason why at higher temperature and at higher temperature we see a higher impact toughness. So this is the study, this is my study. So coming to the summary part, we can make 3-4 important points. One, the nodule size was remained constant, and we saw the change in interlamellar spacing and colony size. The nodule size was constant because we were austenizing it at the same temperature and same time. And at room temperature, we saw the impact energy was unaffected by our interlamellar spacing or temperature, because it was only governed by the nodule size. Whereas when we increase the temperature and when we reduce the interlamellar spacing, we can see higher impact energy. And as the temperature increase, the impact energy become more, because more number of slip systems got activated in cementite. And at higher temperature, we also saw a bigger ductile fracture region in the case of to 590 as compared to 725 at 250 degrees Celsius. That's all. For more, you can scan this and go.